What year?
So YouTube Blade.
1970,
I think so.
1978, 77, 78,
Oh.
somewhere around that sort of period. Dave used to have a big red Land Rover and used to go storming around the countryside in and all sorts of funny stuff. So Dave, Tim and I have sort of known each other forever. And Dave used to work for OTC.
Like a lot of other people in the club,
Like
it seems.
other people in the club. Here comes Dom. Then he worked for somebody else, and then he worked in capacitors. And anyway, he can tell you all that life story. He's going to talk to us tonight about
Repairing power supplies. Look, this has been a bit of stress for me, this one, because I'm not sure how to pitch it and where to pitch it to, and I'm also not an expert on power supplies, so I'm hoping that some people here will be able to help me out from time to time. And I have to say that, I have to say this supply that I've got here that I'm repairing, I started June last year, and then I thought, oh, I've got to put together a presentation today, so I'm whizzing to get the presentation together. I've got to get the supply going, so I turn the supply on and guess what? Doesn't work. So.
And he has been talking about this presentation since about June last year.
Yeah, well, that too. But anyway, thing is, I just want to talk about repairing, how I went about repairing this power supply. I did get it going, but it suddenly stopped, and I think I know why it stopped. But anyway, so step one in repairing. Now, what happened was step one in repairing your ATX power supply.
Dave, can you do me a favour and move closer to the screen so I can get both of you and it?
Yep, I'll try that one. What happened was, last year my father came along and he said, oh, my computer's not working, could you fix it? And I had a look at it and I thought, oh yeah, the power supply's not working in it. And I thought, amateur radio person, able to fix things, $30 for a new one, bought it, put it in, Dad's computer's working fine. So now I've got this power supply in my hands, an old one, and I'm thinking, what do? Hang on, I'm just trying. You fix it.
Take the fan out, you put it on your solar panels and you have it as a fan.
Maybe I should have done that. So, nothing learnt, so I thought, well, replacing it, nothing learnt, so take it apart. So this is a supply that I took apart. It's a Gigabyte part number something or other. And I thought, I'll have a look on the net and get the circuit drawing for it and all that sort of jazz. Nothing there. Had a look at some other supplies on the net, circuits, nothing, doesn't even look familiar with that. That looks weird. So I thought, well, something's different about it. And this one here's how supplies used to be when I last looked at it. And this one's how this one is now. And the difference between the two, I think I need something to point with. An antenna there, Rod. Anyway, the old supply's got two capacitors here in it, for starters, and this one just had one capacitor in it. So I'm thinking, well, what's going on? The old supply has one switching transistor here.
Do a Harry Potter with that.
Oh, thanks, Rod. One switching transistor here, and this one's got
Who was that? Benelec, was it?
something going on, and it's got this weird stuff happening here. So I was wondering, oh, what's going on with these supplies? So I started looking around. But first of all, I had to fix it. So the first thing I did was I obtained an isolation transformer, which I wasn't sure how I should pitch this to you guys, because if you're in silicon chip and everything, you've got to come out with all the safety things. That's my isolation transformer. It's out of an old TV set. It could be, but it seems to have worked fine and I'm still alive. Sorry?
We want to see the smoke come out of it.
Well, I can just show you it on the video. That's an old transformer, and it's got a little 6-volt light which comes on, and it puts out, actually not 240 volts, it puts out about 220, but that's okay.
Question?
Yes?
Why an isolation transformer?
Well, because I'm about to go and start measuring underneath the power supply, and I want to be able to put the lead of the crow, the earth lead of the crow, onto the active portion of the supply. So the supplies will always have a separation between the 240 volt side. There'll be about a 4 mil or a 5 mil separation on the board between the 240 volt side and the output side. So I always use one of those so as I can make measurements on the live side of the supply. So I'll show you, if you want to see it, Dom, I'll show you in the circuit, you'll see it.
That also means you don't fry.
it also means you don't get any frights, and your crow remains intact.
Just
So-
that transformer, because that does 240 to 6 and 6 to 240 or something.
It does 240 to 6 and to 220.
Yeah, okay.
So I'm using a 220 output on it. But if you wanted, I would get a properly made one. That one's 8 years old. It came out of an old TV set. So my first steps in repairing was get an isolation transformer, use incandescent light bulbs as a current limiter for the transformer. This is something which I normally just solder things onto, but I concocted it today. Sorry?
It's like Uncle Fed.
It is a bit. So this is the in, and this is the out, and these two sit in series with the active lead.
So that's the line.
So that's the load, and that's where I plug the suspect supply in, and you plug it in, you turn it on.
Are there any particular value of bulbs you need to use?
Well, you just select. It's selectable. Select on test. So you can plug the supply, and if the bulbs come on, things might not be right. And at least you don't get any smoke in the supply. The bulbs just come on. And Ian, if he's here tonight, mentioned that trick to me. And so anyway, those bulbs have been around for probably longer than Ian has. Anyway, so that's it. So connect all the outputs to a load. I found that for repairing the supplies, now I think somebody had a unit for testing them who was here tonight. Who was that? Anyway.
Oh, no.
Might have been Greg.
You're frightening them off now.
So which one? You want those, some more of those?
Yeah, you have a tester for these supplies. But anyway, I managed to find this on eBay, which I got. And you can plug your ATX connector in there, and it's got an on-off switch. It's not the bee's knees because the fuses are all about 1 or 2 amps, and the supply is supposed to be doing 40 amps or so on some of the outputs. But anyway, it's good enough to load it down, at least get the measurements, and it's got...
It breaks out all different voltages anyway.
It breaks out all the voltages, and you've got a little switch there to turn the thing on and off because there's a green wire through in here, which plugs into here from the supply that disearths, and everything should come on when you turn that on. So I got one of those.
So was that 30 bucks?
But-
That's right.
That was about $5, I think, or something.
The one
Yeah.
I've got costs about 30, and that you just plug everything into it.
Yeah, I might borrow yours.
Green lights or red lights, depending on whether
Yeah.
it's working or not working.
Well, this one's been okay, but the terminal's a bit hard to get into. Anyway, so that was that one. So, and I used a 12-volt lamp as one of the outputs because you say it's using media, you see it come on and all the rest of it. But yours would solve that problem, Greg. So number 4 is the most important one. Ensure you're safe. And the capacitor mains cap on the bulk storage cap on the supply retains voltage, and it can become a bit frightening at times if you're short out. One flash, yes, that's right, or it's ash. So I turned on the supply and checked for B plus across the bulk storage caps, and as it happened when I did it, I did get B plus. I got no light, and I got the B plus on. I noticed that there was.
Blood type or?
Oh no, that B plus I think just means battery positive.
Right.
So B plus is a voltage that should be normally around about 300 volts, 400 volts for the supply to drive the switcher on the primary switcher on the supply. So there was no switching happening. There was no signs of life, except I did have 5 volt standby, which was working.
So no ants living in the supply?
There were no ants. I've had a supply go up because an ant crawled across a transistor. Yeah. And the grounding of the power on signal, that's the green wire on the ATX, just had no effect. So that didn't work. So then what to do? I couldn't recognise anything much from the PCB. As I showed you, it was a bit strange. Didn't have the 2 filter caps. I looked up data sheets for a couple of the important looking ICs. There are about 2 16-pin ICs there. I looked up data sheets for both of those ones. And I discovered that one of the main chips that was on it was a CM6800TX. I think that's the right part number for it. It was a PFC and a pulse width modulator controller IC, power factor correction. And the data sheet for that particular IC showed a ramp that should be present on pin 7 of it, but there was no ramp sitting there, no ramp, so the thing wasn't switching. So I went to eBay and bought a pack of those ICs, CM6800 TX ICs for about $5.
So you bought 5
And-
just in case?
No, your minimum quantity was 5, and they were only $5 for the whole of them, $1 each. So I thought, oh well, if I blow one up,
$10 so far.
it's for fun.
And education.
And education, most importantly, education.
What was the rating of the supply in the first place?
Oh, you mean currents or voltages?
Well,
It was a 470 watt supply all up.
so $40.
Oh, yeah, $40. Yeah, it was a very expensive.
So far. Keep going, David. You're going well.
Anyway, okay, I don't want to bore anyone. Anyway, so the action was there's a ramp on pin 7 and the supply now works, which it doesn't now, but it did then. When at least a 12 volt output is loaded, I noticed that the switching frequency was 300 kilohertz, and I was expecting something more like about 70 to 100 kilohertz. So I thought that's a bit high.
Why were you expecting that?
Well, just because for switching supply, 300 kilohertz is getting up around an IF frequency. I thought that's getting a bit high for a switching supply of this size. And when I looked at the output transformers and things in it, I thought maybe that's a bit high frequency. Someone else might have a comment on that, but
You can look up the
oh,
diodes.
hi Ian.
Look up the diodes and look at the speed of the diodes and
The switching diodes.
yeah, your rectifier diodes.
Yeah.
Obviously if the diodes are slow enough that they aren't going to switch on or off in that at 300 kilohertz, then you can be sure there.
Yeah. Well, anyway, I thought 300 is too high. Anyway, so I went and measured the ramp on the on this IC, and yeah, it was sitting at 300 kilohertz as well. So you know that's what's causing it. And then I had a look at the data sheet more closely for that IC, and it said that the TX has a divide by 4 on its output for the ramp for the switching. So I thought, okay, maybe I've been given the earlier model with the wrong stamp on the top of it, since I got it from overseas.
Is that fake parts?
Well, it might have been fake parts, so I thought, oh well, look, I'll readjust it back down to about 100 kilohertz. So I dropped it down to 100 kilohertz, and it was fine after that.
How did you do that?
On the ramp, it's got a capacitor and a resistor that I'll show you in a circuit in a moment, but it's got a capacitor and a resistor that determines the speed of the ramp. And so I just and they also tell you in a data sheet how to calculate the speed. So I left the resistor intact and altered the capacitor to bring me down in frequency. Oh, I don't know, it's 1,000 picofarads, the one I used, and I think it had a... Oh. I got it out of a junk power supply. And the other problem was, you're supposed to have less than 50 millivolts ripple on it, and it didn't have, it had more than 50 millivolts ripple, little spikes at 50 millivolts. I never actually got to...
The data sheet didn't say what frequency you're supposed to use it at?
Yeah, it said 100 kilohertz.
Oh, okay.
It didn't say you're supposed to use it, it just said example 100 kilohertz, but you know, an example's an example. But yeah. Anyway, so look, before I go any further, I'm just going to start going into the supply itself now, because there are sort of, it's full of buck converters and boost converters. So I thought I might just quickly show a buck converter for those who aren't familiar with it, others are. And I won't try and do any magic explanation of it. I'll just do a hand waving one, because that's probably all I want to get into. But basically a buck supply is one where the output voltage is lower than the input voltage, and the output current is higher than the input current. So in other words, there's conservation of power through the buck converter. So if it's drawing 3 watts of input, you're going to get 3 watts of output, less efficiency losses. So usually they run at about 90% efficiency. So there's 2 switches in a buck converter. This switch is usually a FET or something like that, or a diode. And this switch in this particular one here is actually a diode. Nowadays, some of the ICs use actually FETs for both those switches and control them. Basically, when this switch goes on, the current in this inductor begins to ramp up, the voltage across it immediately that switch closes is the difference between V in and V out. Okay, and the current just ramps up. It hits a set point at the top, at which point the controller that's controlling the switches will decide, okay, time to open this switch. So it opens that switch. The voltage across this inductor is now the output voltage plus minus. It immediately flips. And it tries to maintain current through in the same direction. So this diode now acts like a switch and picks up that current and lets it flow around here and keeps this capacitor charged and the load happy. Okay, so that's about as best I can do quickly for anybody. So switch on, current ramps up, switch off, current ramps down, and so on. Okay, and you can see here that there's an average current. So there's actually in this inductor, the current in the inductor is sort of equal to the load, less ripple and stuff. So it's always got a forward current flowing through that inductor. And the level of that current is from 0 up to this point here with this ripple sitting on top of it. Okay, and the ripple's caused by the switches opening and shutting. So it'll be a very quick changeover from through that direction for the current to that direction for the current. But in all cases, the inductor is storing the energy, right? V out is simply the ratio of the on time expressed as a whole period times the voltage in. So if it's 50% on and 50% off, then V out's going to be half of V in, and so on. That's just a duty cycle. Yep. So anyone want me to go further with that, or I'll just stop? I think I'll stop. So the next one was boost topology. Now there's a lot of buck topology in this switch mode supply. There's also one boost topology in it. Boost topology is slightly different. You now have the coil on the input side here, and the coil current now is, I want to say it's continuous. It's the input current, but the output current's not actually continuous, and I'll tell you why if you pick it up already. When the switch is off, the inductor charges up to the difference between the input voltage and the output voltage through this diode, which is a switch. Okay, and the current in it starts to ramp up. It hits a set point for your ripple. The switches change over. This switch opens, and the current now continues to flow through D1 to the load. So, and while it's doing that, the voltage across the inductor is now swapped. So it's now adding plus minus to V in. So this voltage is now higher than V in. And this switch turns on, this one's off. The diode acts as a switch, it's on now. It goes out here, and the current slowly ramps down through the inductor because it's losing energy and it's dumping energy into the load. Okay? And for that one, for this arrangement, if you go through and do the maths, you get that V out is 1 over 1 minus the duty cycle. So if the duty cycle is 50%, twice the voltage out as the voltage in. At all times with all these things, the power is maintained, so the input power equals the output power. So if you've got a 12 volt input and a 3 volt output, and you've got 12 watts going in, then you've got 12 watts coming out, and there's 4 amps coming out here, and there's only 1 amp going in there. On average, as the thing works. I'm putting people to sleep, so I better move on. So the Gigabyte circuit, this is the one that I actually was looking at, which is this supply, which I'll just drag up in bits and pieces. That's the one that I looked at and couldn't work out what's going on with it. You can see that it's got a single transistor here, and this is, yeah, it's got a single transistor here. Mains voltage comes in through here through a mains filter, through the bridge rectifier just there, goes through a filter network just to stop noise from here going back out. And then it goes through a boost converter formed by this transistor and this inductor. And it boosts the voltage up to go into this bulk storage capacitor, and it boosts it up to 420 volts. So that was the first system in it that I was interested in. So that was power factor correction and bulk storage. The next step that it had in it was it had a 2-switch forward converter, because when I was looking at the supply, I found that that's strange as well, so I'll cover those with you, so they're not bad. And the last one, which was a real ripper, was a 40 amp 3.3 volt post regulator. So I'm trying to think, well, how do you make a 40 amp regulator, post regulator, from a 12 volt supply? You know, with not very big parts. So I was trying to work out what was going on, how that was being done.
Obviously you don't, because if you do, it blows up and doesn't work.
Yeah, well, there's that about it too. So the power factor correction and bulk storage side of things. So the power factor correction circuit is, I said it's a boost converter. It takes current from the input and functions as the input and instantaneous voltage. Why have power factor correction? And that is because on the older version of supplies, they had 2 capacitors and a bridge rectifier feeding those 2 capacitors. The supplier would take energy out of the bulk storage capacitors, the 2 capacitors, and at the top of every 50 hertz cycle, it would top up those capacitors. You must have all seen that with a bridge rectifier, you get the pulses coming through. Well, what happened between 10 years ago when I looked at one and now when I looked at this last year is that some regulation got into the system, and they said, oh, we've got to fix this up, because when you got, I don't know how many computers there are in Sydney on any working day, it'd be more than 5 million of them. If each little peak for that 1 millisecond or 2 milliseconds of that AC main cycle is drawing 1 amp in each supply, that's a whack of unbalance in the supply, 5 million amps each time it does it. So I was thinking, well, that's why they've done it. So they've changed the design they've regulated the design of these supplies get changed so that they have power factor correction on the input. And how it's achieved is by having a boost converter there, and I'll just run through in a moment how that actually does it. But it's pretty interesting. It only needs a single bulk storage cap as well for these supplies, because you get rid of the two. The two on the older supplies were always connected in series, so that they could switch between 240 and 120 volts. So they only need one now, and they put one about 400, I think 270 microfarads and 450 volt one. And they charge that one up, and they charge it up using this boost converter to 420 volts. So they charge it up to 420 volts, so there's a lot more energy in that capacitor than there are in the two in series for the older supplies. So in fact, I worked it out, it's 1.5 times the energy stored in that single capacitor. So they get a bit of gain in that way. They don't have to put an extra capacitor in. So they're losing because they've got to put the PFC circuitry and all the rest of the parts for that, but they're gaining because they can now have a single capacitor rather than 2 electrolytic capacitors for the bulk storage. It's easier for them to meet the power hit requirements because they've got this 420 volts sitting there, and they've got a nice, well-regulated 420 volts sitting there.
When you say power hit, you're talking about a glitch?
Yep. If the mains drops out, PCs have to be, I don't know what the timing is, but they've got to hold up for at least a couple of cycles, I think. I don't know what it is, but I did read it somewhere.
And having those 2 electrolytic capacitors was also a fault area in a lot of them, wasn't it? Because of the amount that they were doing.
Oh, yeah, I don't know. The caps would swell up.
Had a couple of fails.
Yeah.
Yeah, but this one's being stretched to 450 volts.
Well, it's a 450 volts going up to 420. But I think at this stage what I should do is attempt to get into the, show you the circuit. So what I did with the supply is, because I've been on it for ages, I traced the whole frigging circuit. So we've got the...
$20 and about 7 weeks of work.
Oh, but it was interesting. So I'll just show you the circuit. It was really good.
And how much copyright has been breached at this point?
I don't want to discuss that. So now I've got to work out how to get this to appear on the screen. Exit the presentation. I'm just got to work out how to exit. Hang on. Whereabouts?
Yeah, that one.
Press the escape key to the presentation.
So just hold it and escape or something? Or?
Open up the presentation.
Yep.
And press
Escape.
You've got it open twice, so it's trouble.
It keeps doing that.
We'll make that one go away because, well, now I've closed it properly, sorry.
That's all right. Right. Okay, good. Thank you. Thanks, Mike. Okay, so question is, can I make this zoom up so as you can see it?
Maybe hit control and use a scroll wheel.
Sorry?
Hit control and hit the scroll wheel.
That's better. And now I've got to move it around with a hand. So where do I get the hand? No, I've got to use a hand. Where's the hand thing? Tools. Tools,
What do you want to do?
zoom,
Scroll around? Use
and
the
tool.
arrows down the
Got it.
And your mouse wheel to zoom properly.
Yeah, okay. Oh, that'll do. Okay, so what I've got here is got the mains input on the left, bridge rectifier sitting here, line filter to get rid of noise going back that way, and then over here we've got the bulk storage cap sitting here, and here we've got a boost regulator. So you've got the inductor sitting here, the on-off switch here, and the diode, the one that I showed before. And you've got the control coming down happening from these two transistors down here. This is just switching this switch on and off. Now how this works for power factor correction is that there's an IC sitting down here that's monitoring the output voltage, the B plus voltage, and it has a, monitors it, this is this 6800 one that I was on about. B plus comes in here and it's monitored here. The other bit of information this IC gets going into it is the ripple from the bridge rectifier over here.
And it tries to draw power through the whole cycle?
Yeah, at this point here, this comes down here, jumps into IAC, and also VRMS comes in there. So this IC knows the output voltage on the cap at the output. It knows the bulk storage voltage on the bulk storage cap. It also knows what this voltage here is doing. This voltage here, that cap's a very small cap, I think it's just for noise. This voltage here basically is half-wave rectified pulses. So the switcher here runs at the same frequency as I set it up for, 100 kilohertz. So these pulses are running one every 10 milliseconds. So what this is doing is it's looking at the voltage and it goes, oh, it's 0 volts, it's 1 volt at present, 1 volt across the sort of load I want to hear will be drawing this much current, so it leaves it on for a very short period of time, or actually a long period of time for 1 volt. And as the voltage here increases, it adjusts the pulse width here to make it smaller and smaller and smaller as the voltage gets bigger up to peak. Basically what it's trying to do is this regulator here is keeping the current constant throughout the whole of each pulse at this point. And it's doing that by adjusting a pulse width on this transistor, right? And in that way, it's eliminating the situation where you've got just the peaks of each pulse drawing peak current, and that's how the power factor correction works. I didn't know about that, so I've learnt that.
Power supplies that had passive power correction, they just use a very large inductor.
Yeah.
Instead. A big iron core inductor.
Yeah, and they've obviously looked at it and they thought this is a cheaper way of going about it. Possibly better, I don't know. It hasn't failed in this case, it's something else that's failed, but anyway. Well, this failed. The controlling IC failed, I suppose, in this case. But so that's how the power factor correction works. At the same time, there's another control circuit embedded in this thing that's looking at the voltage across the storage cap. So it determines how much current to draw from each of these regulated pulse widths, the amplitude of it as well. So obviously as the PC decides, or the load decides it wants more energy out here, each of these little 100 kilohertz pulses are being drawn throughout the whole of these rectified pulses here, just get slightly wider. And so it basically makes the input to this look like for a resistor for the whole pulse coming through. And it's doing it so fast, it gets away with it with all the filtering going on the way out. So that's how the power factor correction, the basic way it works. There's a bypass diode here, I'm not sure why that's there. At first when I looked at it, I thought, oh, when you first turn the power on, the current can go straight through there and charge this up at least to the 240 volt, root 2 times the 240 volt, whatever, 380 volts or something. But it can do it through there just as well, so I'm not sure why they put that there. But some
could be when you turn the power off, you get a pulse back out of the...
Yeah, L5 will be charged positive on pin 4, so that dial will be reverse biased.
Oh, this one?
No, the top diode.
The top diode.
If L5, pin 4 will be positive, isn't it?
Well, this voltage here will always be... yeah, okay.
It's a boost converter, so pin 4 will be positive.
Yeah.
So the diode at the top of the screen will be reverse biased, so
it won't do anything. It's only on during startup where it becomes forward biased.
Yes, that's right. Yeah.
And I'm thinking it's there for some startup reason.
Yeah.
But I'm just thinking, well, why have it? Because you've got the inductor here in this diode, it just goes through there anyway.
Current surge into the big capacitor from the switch.
Yeah, they'd have a reason. Anyway, so that's the power factor correction side of things.
Maybe they just had too many diodes.
Why do you think the IC would blow? Because that would...
Why did it blow?
Yeah, because that would seem to be, in a pretty comfortable environment compared to some of the other stuff.
It is a very comfortable environment for the IC because it's got, if you look down here,
Maybe it just gets hot. Maybe it's in a hot environment.
it could have been heat, could have just been, I don't know. You got a 100 ohm buffer resistor here and these two driving. Why does any IC go, I'm dead? Yeah, maybe a lightning strike. I don't know. A spike. Anyway, so that's the first thing that really got me interested was the power factor correction in this thing. And it's now in all switch mode supplies, ATX supplies for computers.
So you put the IC in a socket in case it goes again?
No, I haven't. I'm pretty good at unsoldering it though. Anyway, so now just go back to the PowerPoint if I can. Sorry? Okay.
So Dave,
Yeah?
you could send that circuit to the Chinese and they could build these, mass produce them.
Well, if anybody wants a circuit, they're welcome to have a copy of it.
Actually,
Go to the page and then press the present button.
Just hit
Go
that.
to the page you want,
Oh, okay.
wherever you got up to. And press the present button bottom right.
Righto. And then hit the present. Do it. Okay. So the next question I had was the next stage in the supply, and this is I needed a circuit again. Should have stuck on the circuit. Or not.
Do you want me to drive and you talk? How about that? Tell me what you want.
I want the circuit on. Dead on. Yeah, sorry guys. So anyway, what I was going to say is that the 2-switch forward converter, I was expecting just a single switch. And when you look at the circuit for this supply, it's got 2 FETs in series driving the primary of the main switching transformer. And I'm thinking, well, why have you got 2 switches in series when one would do just as well, and all the old supplies all had one on them anyway?
It's a very common topology in things like Sony TV sets, and I think it's
To have,
the transient voltages between them.
yeah.
Usually on Sony TV sets, they're actually driven, the base or the control, the gate is driven by a couple of windings on the transformer.
Well, this one has the gate, thanks Mal, over at the switching, yeah, this one. So this transformer here is the one you were just talking about, Ian. This one drives the two FETs.
Yep.
So you got the B plus sitting here. This is the primary of the main transformer. You've got a FET here and a FET here, both being driven by floating gate drivers, and both controlled by 100 ohm resistor to that IC on its PWM control. And what this IC is doing now is it's got an output, the separate output here is PWM out. And that's driving this one, as opposed to the other output that's driving, at the same time driving the power factor correction. So the advantages of having these two apparently is that with these ATX supplies, the efficiency is one of the main things that they had to meet. And there's some criteria, I could have quoted it last year, but there's some spec they've got to meet. And it's efficiency is high up in the spec. So what happens with these two, switches here is, I think I have a nice circuit showing a breakdown of the actual.
It's magnetics and 2 switch.
Yep, that'll do. Try that one. Yeah. Okay, so this is the arrangement that it's got. Basically, taking away all the other junk. You've got Q1 and Q2, anyway, 2 transistors here. You've got 2 diodes and the B plus supply here. So these both switch on together at once. So when they both switch on, you've got B plus applied across the primary of your switching transformer plus minus. And that's fine. The current there ramps up and it's monitoring the current. I'll show you on the other supply there's a return resistor here and it monitors the return current. That's the 6800 that monitors it. So the current here will ramp up, and then at some point it will switch these both off together. And as soon as it switches those off, the voltage on the transformer flips, and any of the magnetizing inductance or stray inductance in a transformer that's using energy that causes the ringing that you get with switch mode supplies is all dumped back through these 2 diodes into the storage cap, so it's not lost. Previously they used to put a snubber network across there, and what would happen is that the snubber network will get hot and you'd lose energy in that. So that's one of the advantages of these things. The other advantage of it is that the maximum voltage for both these FETs doesn't need to be double the supply which it does for a single one. So they can get away with a lower voltage rated FET for these things. So that's another reason that they do it.
Lower voltage FETs have a lower on resistance.
Lower IDS.
So reduces losses.
Yeah, lower RDS on. Yeah, for the same thing. So yeah. So that's why they're doing that arrangement. So I thought, well, that was interesting as well, because I hadn't, I'd seen single-ended output ones. The second thing that was interesting was the fact that it's a forward converter. So what happens here on the output of this transformer here is the voltage here is going plus minus that way. These dots indicate that when this is pos, that's plus. So it dumps the current through into this inductor and capacitor here, and what we're looking at here is a buck converter. Because when it's sitting plus minus, this switch is on and that one's off, and when the output flops the other way, in other words when it's discharging through these diodes, that switch is off and the voltage across this one flips and that's on. So this is actually a buck inverter. on the output of the supply. So this diagram here shows it with the two FETs on. You can see that it's chucking current out that way. When the two FETs switch off, the current goes through this diode and chucks it to the output. And then all it becomes a matter of then is monitoring this output voltage here and altering the pulse widths on the 6800 at the start. So if I go back to the main circuit, thanks very much. So you can see here's the two FETs. There's one of the catch diodes and there's another catch diode for dumping the energy back into this cap. Down the bottom here is a current sense resistor, and off here goes down to that 6800 where it goes to a current sense input, and it decides when it's time to switch this off and change it based on that current pulse. Over this side here, maybe if I look at, looking at this place here for starters, if you look at that, straight away you go, well, I do now, straight away I go, oh, that's a buck inverter. We won't worry about that other coil winding on there just for the time being. You go straight away, oh, that's a buck converter, because you've got the output here to ground, driving positive here, then it flips and negative, and it's dumping, storing energy in this inductor, then dumping it into this 1000 mic storage cap and this filter network here, and that's our plus 5 volt output at that point. So then up here is plus 12 volt outputs are up here. There's another buck inverter sitting up here. This time this one is driven from this winding. It's a higher voltage, so large number of turns on that winding. Same setup, two really heavy diodes sitting there on a heatsink, and it dumps the energy into this inductor and through this filter network here, storage, large storage, and then you've got two outputs here, a 12 volt one, a 12 volt two. I think it's really, one's the white and one's the yellow wires going off to the ATX supply. I think the yellow wires go near the PC there for something. Obviously I don't want noise from this supply getting onto this supply, so that's what all that's about. These are just two vertically sitting inductors wound like that up in the air and straight down. They're air cored, there's no magnetics in them.
Maybe one for audio so that you don't hurt audio and so you don't get switching noise and digital noise on there's any
across
sound cards and things.
Yeah, that's possible. Yeah. Anyway, so these are all bifilar wound on the one toroid, by the way, these windings. So I'm guessing that there's induction from when this one here is charging up, when the magnetic flux in this core increases. This one here goes plus minus, and they're using that to provide a neg 12 output here. Now the neg 12 output there, as far as I can tell, is not actually regulated. So I'd say what's regulating it is regulation on this 5 volt and on this 12 volt. There is some regulation on a 12 volt as well, I think, but certainly there's.
Use plus or minus 12, is that right?
I beg your pardon?
CD drives used to use it.
Yeah, CD drives probably do.
Also serial ports.
Oh yeah, classic.
Yeah.
I don't think anything much uses the minus 12. It's not these days.
It's there just for legacy purposes.
And I don't know why these two are coupled. I'm thinking maybe it's because the 5 volt is definitely being regulated, and it may be that as the load changes on this one, then the pulse width here becomes greater to manage it. This might be set up to sort of counteract that effect. I don't know.
Load balancing or something.
Yeah, it might.
The 3.3 that's regulated. The 5 volts is just
Well, the 3.3 I'll get to next for the regulation.
above 3.3.
Usually they regulate 5 volt and the 12.
Well, on this one, if you move in the circuit, you can see where I think. Hang on, just across that way a bit. So 5 volts standby, but there's a 5 volt. There's a 5 volt regulation happening somewhere. There's a 5 volt adjust pot I found.
Drop down a bit.
Down's going no, that's all supervisory and stuff. Yeah, no, that's for the fan. That's the supervisory sub-circuit, so that's nothing to do with it. Down a bit. Where's the 5-volt regulator gone?
Should be somewhere near the octave.
Just going to go to the left.
That might be the problem, it might be missing.
That way, I think, Mal.
Yep.
Yes, 3.3, further 5 volt. Oh, don't tell me I can't have missed it. Ho hum. I wonder what happened to the 5 volt one. I'll have a look.
Where that one goes, perhaps. Where the 3.3 cents goes.
That's the 3.3. There's an adjustment pot for the 5 volt one.
Could be part of the supervisor.
Maybe I drew the circuit up in such a hurry today I missed it. It's got to be here somewhere. Must be on page 2, yeah. No, that's the 3.3. Oh, well, sorry about that, guys. The 5 volt seems to be missing. I'll have to fix that one before I send it off to China. That might be it.
5 volt, 12 volt adjustment.
Yeah. Yeah, this is it. Sorry, it is from the supervisory circuit. So basically what happens is plus 5 volts comes in here. And they really love these TL 431s. So they have a reference here of 2.5 volts on their terminal at that point there. So these two resistors here and things are set up so that when it's at 5 volts, that's at 2.5. If it goes higher than 5 volts, this thing turns on. It goes back to VDC, which is an input on that 6800 and tells it to alter the pulse width, and vice versa. This takeoff here is part of this circuit over here that monitors the 5 volt rail and switches the supply off if it doesn't like what it's seeing there. So that's the 5 volt controller. Righto.
Back to the presentation.
Back to President. Sorry?
That'll be for USB.
I think the USB actually uses a 5 volt standby on this supply, because when the PC is turned off, they've still got the voltage on the USB. So I think I covered all those things: leakage inductance, energy turn to bulk, storage, blah, 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 blah. 2-switch, yeah, and Gigabyte circuit. So we've had a look at that. Okay, next one. So the next one of interest, so that were the first two things, was the power factor correction and the fact that they had that forward converter with those two switches in series. And the third one is how on earth you do a 40 amp post regulator at 3.3 volts. And I'm thinking, well, you know, I mean, I've heard of, you know, little 3-terminal regulators and things, but how do you do it? And what do you use for a switch? So it turns out, it's a pretty cool trick. They're using I suppose a magnetic amplifier people seem to use, but I tried to find out about them, and the best I could find out is that one was used in a V1 bomber. You know, those V1 rockets, they used them as early as then.
They have been used, they were used in valve gear as well.
Yeah.
Yes,
Very old technique.
And also subsea cables. If you talk to Ross, he used magnetic
Amplifiers in those.
Yeah, so the
Well, this one is sort of a magnetic amplifier. Anyway, basically it's a very high current switch with a controlled on delay. And it's a very low control current that's used to control it, only a couple of milliamps. And the transistor that controls it is a TO92 package, series pass transistor. That's one of the little 3-terminal critters. And it has a minimal component count. So at this stage, well, I'll refer to page 46 of magnetics. So what we might do is go to, let's go to the Gigabyte supply again, go back to the main circuit again. So if we go up to the, and back this way a bit, yeah. So this is a 3.3 volt output, here's a 3.3 volt sense. they run a separate brown wire out that goes out to the connector that plugs on your ATX board for the 3.3 volt sense. The thickness of the wire going to the ATX board ain't a 40 amp wire. So anyway, there are a number of other 3.3 volt wires running off around the place. I don't think it ever uses 40 amps. If you have a look at the circuit here, everything looks normal from this point further on to an extent, because you've got the transformer output here flipping all the time. You've got an inductor which is actually being used as a switch, so I'll get into that in a moment. And you've got the voltage here flipping positive and minus, and you've got here a standard buck converter arrangement, right? And that's controlling this, that's producing a 3.3 volts out here with this buck converter sitting here, and then the filter system afterwards. But then you've got this rigmarole going on here with another TL431 and a TO92 transistor, a really small one. And you've got this inductor here, L30, which is a ripper of an inductor. It's a real little thing. It's just, this particular one's, it's to do with the magnetics in the thing. I don't know enough about magnetics to say exactly how they've rigged it, but it's that one there with the yellow core, that inductor. And what happens is, when this goes plus, that inductor is intended to saturate the core. So when this goes plus, the current starts flowing through it, and it moves up the BH curve till it hits saturation for the iron in the core, and whang, the current goes straight up because it's just hard on. So that's a switch now which is just switched on. And to determine, so when this goes positive, the voltage here jumps up straight away, the current ramps up slowly. It's probably only about 50 milliamps or something ramping up. It suddenly hits saturation, and bang, 40 amps or whatever's required will flow straight through there because it's no longer an inductor, it's just a bit of wire. So what they do then is, when this goes the other way around, minus plus, this inductor here comes out of saturation and it moves back down the BH curve. And how far it moves back down the BH curve is determined by the small amount of current that's packed in here through the inductor in the reverse direction. And it moves it, and this keeps a current flowing in this core when the voltage here is reversed. And what that does is, it sets a start point for when it next flips. So the start point might be way down the BH curve, in which case it'll take a long time, relatively speaking, before it saturates and bang, switches on. Or alternatively, if this current's kept high in the return, it'll take a very short time before it switches back on. So effectively what's happening is, that the input to this buck converter here, you're altering the width of the pulse, that's the on switch, the duration of the on switch, by varying this small amount of back current flowing into that inductor. And I thought that's really amazing that they do that, and they get away with it. And this is a sense coming in here. It actually picks it up from there through this resistive divider here. 2.5 volts across there onto the output of the TL431. If this starts going too high, it switches on, pulls on that, puts more current through, delivers more current. And it's coming from the 3 volt supply here through R30 into that inductor.
So what's the amperage rating at a 3 volt 3?
The 3.3 volt line is, I forget what it is, I think it's 40 amps.
An old ATX.
30 amps.
30 amps at 3.3 amps on this one too.
Yeah, 30 amps on it. So that I thought was pretty amazing.
Old processing.
Yeah. So we'll go back to the PowerPoint.
It's just about everything now runs a VRM.
Well, hang on, just stay there for a tick, Matt. Oh, that's right.
On the motherboard.
So everyone happy with that explanation? It's a bit of a hand wave, I know, but I thought, well, that's pretty interesting. So go back to the PowerPoint now. you'll get there. So it's a very high current switch. So that's what I was talking about there. Very low current, a TO92 package to control it, and component count. I could go and show you the BH curves for it if you wanted to have a look, but I mean, BH curve's a BH curve. Yeah, or maybe it's a 30 amp one in this case, but still very damn high current for what it's doing.
100, even at 30 amps, that's 100 watts.
Yeah, yeah, it's a lot. Unfortunately, if we move to the next one.
It's targeted for supplying old CPUs.
Yeah. So that's my summary. The repaired supply is yet to be used on a real computer. And by the way, it doesn't work now because it didn't work. I turned it on today. I started all this about June last year. Anyway, it was an interesting journey and I hope you enjoyed it. And I've got a nice circuit for that power supply if anyone wants a copy of it.
You want to sell it on eBay?
Complete with 5 volt. I'm thinking I should load it up on some website somewhere. So
sell it on eBay.
Just slides in the couplet side.
I beg your pardon?
Can we put the slides on the couplet side?
Yeah, sure.
What did you repair?
I suppose.
In case I come across
Why?
Gigabyte supply.
Like it didn't work and then you repaired it. What did you
Oh.
actually do?
Oh, the repair was basically the replacement of that 6800 IC at the start. But now, I had the whole thing apart because I was tracing the circuit. If we go back to the other circuit, if you want a bit more.
Why did it fail?
I don't know why that IC failed in the first instance. It could have been. I couldn't see any little burn marks or where something might have flashed across on the board or anything like that.
Had a time to live setting.
Well, it's in Dad's house. Something happened with it. The other thing about the supply, by the way, is just that over this side of things is this other little IC, which was a bit of a. This one's a bit of a problem maker. This supervisory sub circuit. It plugs in a separate little thing, and it's got this IC in it. And basically, it takes all these voltages into it. It's only got 2 outputs on it. One is the power good output, which goes to the ATX connector. I think on this side over here, I've just said this is all ATX connectors. So the power good output goes. And the other output is this fault protection output, not. Basically, it sits low when everything's happy, when it's happy. And that keeps the supply. So at present, when you earth this power on here, it applies an earth through to here. This thing here is getting its VCC through this 100 ohm resistor, which comes from the 5 volt standby supply, which is running all the time in this thing. I didn't cover that, but I won't go over it. It's there if you want to have a look at it. There's also a 15 volt supply that sits there all the time as a result of that 5 volt, as part of that 5 volt standby supply. And the 15 volts sits on the other side of an optocoupler that's over here somewhere. I better not touch the screen while I'm moving my finger. Now that's the wrong optocoupler though. I have to go up that way a bit. This is it here. I think that no, that's a 5 volt standby. This one here. This is it here. This one here has this output. This fault good output comes out. It says fault protection output. Anyway, it's low when it's good. So it drags on this opto through the 5 volt standby supply and keeps this turned on and pulls this 15 volts, which is coming from the active side of the board, because this is. I started off by saying the board's all separated. The magnetics are separated. Well, all these supplies, for anyone who doesn't know, they're always separated. So the ground on this side of things is the ground that people are touching, and the ground on the other side is the ground that you don't touch. Anyway. This plus, that's what this opto is doing, it's providing that isolation across it, 15 volts there, and that just goes to that IC, the 6800 IC, if we move across to that one.
And shut it down for stand.
Yeah, and just shuts it off, so that comes in here, the VCC for it just turns the supply rail off to it. And presently with the supply, when I go to switch it on, the power supply comes on for a moment and goes off straight away. So it's this supervisory circuit shutting it down, and I actually think it's a problem with a 3.3 volt output, but anyway, I'll get onto that later on. So that's how the thing boots up, starts up, and the 15 volts to drive that comes from this switch here, which moved across that way a bit. Yep, stop. That's always got B plus on it because we've got that bypass diode I showed you up on the power factor correction circuit. So that cap's always charged up, not always to 420. When the thing's in idle, it's just charged to √2 times the mains voltage, RMS mains. And this here transformer's got a separate winding here which produces a 15 volt output here, which is always present and ready to be applied to that as a VCC to that thing when it's running. Anyway, so that's it.
You hand trace that? Just a quick. That circuit you hand trace?
Yeah.
So how did you know where the transformer works?
Oh, I took the transformers out and put a signal into them and measured and had a look at what the polarity on them was.
Polarity of the phase. Yeah,
yep. I also, as I was doing it, I also looked at...
I wonder it's taken you 12 months to get this far.
Well, I wanted to find out exactly what it's doing. The other thing I worked out was the turns ratio on, not that transformer, but on the main transformer. I worked out...
Which software did you use to draw the circuit?
Oh, Eagle.
Okay.
Yeah.
Now we've got a few other questions, I think.
Just a comment on the isolation transformer for anybody who does this at home. Look, the commercial ones have always got one outlet on it.
Has what?
The commercial isolation transformers have
Yeah.
got a single outlet only, and warnings all over them not to connect multiple outlets. So I noticed you had a double G on that because that's what you had.
Yeah.
But you probably should tape over it, and the reason for that is so you don't connect a second bit of gear, which is earthed, and lose your isolation.
Oh, I see.
So it's really, really important, if you do make one, just have a single outlet only.
Oh, maybe I should...
Any of your test gear, obviously all your test gear wants to be floating, because you've got to keep the whole thing isolated.
Yeah.
Anyway, it's just a comment, but you will see on the commercial ones, one outlet and big warning.
So I should remove that switch plate and put a single outlet there. Yeah, I only ever use one on it anyway for that reason, but...
I know why you did it.
Yeah, and I'm not going to loan it to anyone.
So it's just really important.
Yeah. I'll do that because I've had that thing for a long time and I've never wanted to use both, so I should do that. I should do it.
I've worked out why your touch screen's got a delay. Because Mel does everything through a satellite circuit and you cannot change the laws of physics.
So you do it through satellite or via moon now?
Any other questions?
Longer delay.
Did you check a common issue that I find with switch mode power supplies in general is poor quality electrolytics?
Yeah, and I
particularly small ones, 1 mic, 10 mic, up to 100 mic. Any of the really small sort of cigarette button, smaller sized electrodes are automatically suspect. And
I haven't.
Amazing how much smoke comes out of the silicon when they fail.
I haven't had a critical look through the circuit to find if any of those are in an important position, but I don't recall seeing them. I think mainly the ones that are electrolytics are all the big 1,000 and 2,000 mic ones on the output, and they're very low ESR anyway, and I just don't...
Yeah, no, as long as they're not bulging or...
Well, they're not bulging.
Any movement when you touch them is suspect.
Yeah, no, they're...
5 cents each might just throw his budget right out. Might just push him over the edge.
Well, I've actually bought a whole lot of them anyway, just in case, but I haven't used any of them.
So what's the estimation on the cost value to repair this supply?
$35. Oh, we won't. The time was fun. The time was fun.
Well, I think we should...
Anyway.
I also have it on good authority he's working on a 9323, so we look forward to the lecture on repairing that.
No.